All right, so we ended the last lecture talking about rejecting or accepting the null hypothesis, and basically we were talking about alpha, which is the probability that we would be making a mistake if we were to reject the null hypothesis. And essentially, the conventional level, like I said, is 5%. When we make a prediction that is directional, that is when we expect that the sample mean will either be higher or lower than the population mean, we can use a one-tailed test, which basically says that the rejection region is within this part of the distribution associated with 5% of the sample, or would be on the higher end if we're predicting an increase. Whereas if it's non-directional, we split that so that we maintain our alpha level at 0.05, but the rejection regions themselves are smaller because there are two of them, one at the lower end, the lower 2.5%, and one at the higher 2.5%. And I think this will all sort of begin to make sense as we actually start conducting statistical tests and really looking at critical values and obtained values and how they fall within these rejection and acceptance regions. Okay, so there are two different types of errors. So I mentioned that alpha really is the degree to which, or the likelihood that we are going to be making a mistake by rejecting the null hypothesis. And there really are two different types we can make, two types of errors that we can make when we reject the null hypothesis. So um, if we fail to find a difference between the two means, and therefore we fail to reject the null hypothesis, that's the correct decision, right? So the null is true, meaning that there's no difference between the two groups, or in this case, that there are blue M&Ms in the barrel, and we say there are blue M&Ms in the barrel, that's the right decision. If the null hypothesis is false, if in fact after we look at the entire barrel we never find a blue M&M, and we say that there are no blue M&Ms in the barrel, we reject the null hypothesis, and that is the correct decision as well. But we can still make a type 1 or a type 2 error. And one would be considered kind of a false positive mistake, and one would be a false negative. So if we look on this side, a type 1 error is when the null hypothesis is true, but we reject it. So if we look on this left-hand side, we have a doctor talking to a male patient telling him that he is pregnant. So he's basically saying that the null hypothesis is false, right? The null hypothesis in this case for this man would be that he's not pregnant, saying that in fact he is pregnant. So we reject the null that he's not pregnant, but we're making a type 1 error, right? So we're essentially making a false positive statement, right? We say there's an effect, but one doesn't actually exist. Type 2 error, on the other hand, is when the null hypothesis is false. So in the case of the M&Ms, right, where we said that there were blue M&Ms in the barrel, but there actually weren't any. But somehow we fail to reject it. We think we saw a blue M&M, but we were wrong. Then we're making a type 2 error. And the example of this is there's a very obviously pregnant woman, and the doctor is looking at her and saying, "You're not pregnant." Right? So in this case, the null hypothesis is that you're not pregnant. The alternative hypothesis is you are pregnant. And the doctor says, "Oh, but the null hypothesis is true. You're not pregnant." And we're failing to reject it, even though it's quite obvious that the null hypothesis in this case is false. All right, so type 1 error is a false positive mistake. Type 2 error is a false negative mistake. So researchers really have to make a decision about whether or not they want to, what type of error they're willing to accept. And the alpha level that they choose reflects their preference for the type of error they want to make. So if we were to increase alpha from a 5% chance to a 10% chance of making a type 1 error, we would then increase the risk of making a type 1 error, right? Because we have a greater likelihood that we're making a mistake by rejecting, because we have a greater opportunity to reject the null hypothesis, right? Our rejection region gets larger, so there's more values that will fall within that rejection region, meaning that we have a greater chance of making a mistake. On the other hand, if we decrease alpha from 0.05 to 0.01, making our rejection region much smaller, making it harder to reject the null hypothesis, then we increase the risk of making a type 2 error. So in this case, then we have to determine which error I'm willing to make, and I will set my alpha accordingly. So, for example, if you have a disease that has no available treatments and the drug you are testing has no side effects, you may be more willing to make a type 1 error and set your alpha level higher, right? Because it's more important to find a treatment for this perhaps fatal disease. And we don't have to worry about the potential side effects associated with the medication because it doesn't have any. On the other hand, if you have a drug with very serious side effects, maybe people die from taking the drug, then you're going to want to you want to make sure that the drug is effective before you start giving it to patients. In this case, you're going to be much more willing to make a false positive error, a false negative error, right? Where you're saying it doesn't work even if it does, because the risks of patients dying is so great that you want to make it harder to reject the null hypothesis. So in that case, I would select an alpha level of 0.01. All right, and so like I said, based on kind of the stakes in the research, I have to decide, am I more willing to make a false positive mistake, a type 1 error? Am I more willing to make a false negative mistake, a type 2 error? And it really depends on sort of what the research question is. All right, so finally, and your textbook goes through this very nicely, there are 4 steps in the process of hypothesis testing. The first, which we've gone over, is to formulate a hypothesis, and in this case, you're going to specify both the null and the alternative hypotheses using the symbols that we've discussed. You're going to indicate your alpha level and determine your critical values, right? So unless I tell you otherwise, you're going to be using, or your textbook mentions otherwise, you're going to be using 0.05, and you're going to use the tables in the back of your book in order to determine what the critical values are that are going to serve as the boundaries for your rejection region. Then you're going to calculate the relevant statistics. In this case, we're calculating z-tests, but we're going to be learning z-test, t-test, f-tests, Pearson R, and chi-square tests. And then we're going to make a decision and report the results. So the decision is whether to accept or reject the null hypothesis based on whether our obtained value exceeds our critical value or not. And then we're going to explain the results in words that your grandmother would understand. And those are the steps of hypothesis testing. All right, so subsequent lectures are going to kind of illustrate this process with the z-test. And as I said, go back to that initial example that I gave you in which we made predictions about whether my class had attitudes that were improved relative to the overall population's attitudes towards online instruction.